So for the next little bit here, we're going to be talking about some higher-level statistical measures that we can use to assess the sort of higher-level behavioral factors associated with participants in our study. The idea here is to be able to derive high-level classification mechanisms, or at least medium-level classification mechanisms, that will allow us to reliably estimate the state of a given person with respect to certain common characteristics or certain common states. For example, we might be interested in on-person, off-person, whether a phone is currently carried on-person or it's simply off-person sitting in a backpack or on the table. We may be interested in understanding whether a person's sitting, standing, lying down, given that they're in some sort of sedentary situation. We may be interested in understanding if someone's in a vehicular context or not, whether someone's likely to be engaged in smoking behavior or not, or otherwise whether a person, whether a pair of people is likely to be in nearby contact or separated, in fact, by a wall. So these are sort of examples of high-level types of labels we'd like to put onto features of the data. And I'm going to be talking about some of the techniques we've used to address some of these challenges, and more broadly giving you a look at three techniques that you might consider within your work. So just as a motivational comment, often to secure high-level insight as to health behaviors reflected within our data, we'll seek to understand and label patterns of common behavior. I just mentioned a set of them. There may be others that are topic-specific for your area. For example, for Cheryl and Joe, classifying whether someone's likely to be eating or not based on whether they're in a certain establishment, they're in a sitting position, an eating establishment, they're in a sitting position, or what have you. Others might be interested in aspects of transportation options, and we might classify whether someone's in a bus or not. Now, we do this for many reasons. In some cases, we're trying to develop hypotheses, dynamic hypotheses involving causal pathways, and we're trying to identify features of the situation that are associated with those pathways. In my first talk for this group, I gave an example of an intervention that was undertaken through the Moving to Opportunity program in the States, a housing voucher program. And we were interested in knowing whether the outcomes secured through that program, positive for teenage girls, were predominantly driven by changes in use of recreational ball courts and playgrounds and other amenities, higher use of sidewalks, whether they were associated with higher levels of frequenting of grocery stores and other markets offering fresh fruits and vegetables rather than convenience stores or restaurants, fast food restaurants. All of those descriptions posit some sort of high-level health behaviors that are not going to be staring at you directly from the cacophony of numbers that come from these devices. In those tables we looked at yesterday with Tableau, there was no column that indicated whether someone was in a fast food restaurant or not. There was no data item for each time point that indicated whether someone was eating, whether someone was on a sidewalk or not, whether someone was in a grocery store. To arrive at those high-level sort of identifiers, we need to do some work, high-level labels. We need to do some work with this lower-level data to take it up a level. And we seek to place labels on the data that will be indicative and that will help us reason about our hypotheses, about our research questions. In other cases, we will use classification mechanisms to help arrive at better estimates for other models and to calibrate dynamic models, which I'll be talking about this afternoon. So how do we go about working with this sort of data? Well, one of the ways that we'll talk about gaining insight into these high-level labeling of low-level data is to actually perform experiments that seek to gather labeled data, what we call ground truth experiments. And back there, William, and also in the back row, Narges, have been pioneers in leading these sort of experiments for our group. And I'm going to be showing some visuals from Narges' work, which show differences between individuals who reported being in an interval of smoking versus those who reported being in an interval of non-smoking. The smoking, those data points that are drawn from smoking intervals are shown in orange up there, and those in non-smoking intervals are shown in blue. And the graphs here, which are from Narges' work, show a set of data in terms of histograms from 3 different types of sensors, all shown in a univariate fashion. We'll be looking at some bivariate and even multivariate data in just a bit. So this is an indication, for example, of GPS accuracy, and you'll find that, for the individuals surveyed, there were many areas of overlap where we were seeing sort of similar counts from the 2 data sets. But here, for individuals who were smoking, the accuracy, the readings tended to be more accurate. Okay, in other words, they had smaller standard deviation measured in meters estimated for the GPS readings. That sort of observation will often result from an individual who is, anyone want to guess? Outside. This is an indication that they're likely to be outside. Another sort of classification mechanism was looking at issues of GPS speed, and here we have a greater predominance proportionately for amongst smoking individuals of sort of not really going any place, sort of maybe pacing around, staying in the same basic area, but not moving at higher speeds or with sort of faster recorded movement. This is RSSI levels. These are received signal strength indicator associated with Wi-Fi connectors, and here you see a somewhat of a predilection. The picture is much more mixed here, but somewhat of a higher proportion of low signal strength indicators. In other words, very weak signals associated with individuals who are smoking. Again, sort of along the lines of those individuals may be outside and therefore in less close proximity to the actual Wi-Fi routers. Looking at this in a bivariate context, Narges created some graphs showing sort of distributions of several accelerometry axes where you can see a fair degree of separation between these groups. There's not to say there's no overlap, there is, but there are some distinctive patterns here, for example, in terms of the accelerometry data, and even in terms of the gyroscope data, there's somewhat different patterns associated with smoking and non-smoking. This is a multivariate graph, which is a little bit more confusing, but shows 2 axes on the X and Y location, on the X and Y axis, and then using sort of more symbolic notation, sort of an indication of speed. The point is that as we examine multiple axes, we may recognize some differences in terms of the distributions associated with this sort of data. This is from a graph associated with two elements of accelerometry data and gyroscope data, where you can see some differences in place between the patterns that result from the data collected from smoking versus non-smoking patterns. So given these sort of empirical data, given the fact that we have these labels we'd like to place on data in terms of high-level health behaviors or high-level aspects of context, inside, outside, whether someone is smoking or not, whether they're likely to be taking a meal, etc. How can we go about classifying them in a more robust fashion, going beyond sort of ad hoc looks at particular subsets of data? How could we go and start thinking about leveraging statistical mechanisms to classify this data? That's what we'll be attending to next, with the provision or with awareness of the fact that the data is suggestive of enough distinct patterns that we have some hope of actually emerging with effective classifiers. And I'm going to be talking very briefly here about three major methods for classifying these sort of data and giving a brief glimpse of each of them. So two of the techniques are going to be techniques that put aside the temporal context, that deal with each data point, each set of observations across multiple sensors in isolation, and try to classify that based on several different readings. All three of these techniques are, in a certain sense, sensor fusion techniques. They bring together data from multiple sensors and try to render a classification. But these first two do so without taking into account temporal context, and this latter one does take into account temporal context. So the first of them that I'll be dealing with is a naive Bayes classifier. And the idea here is we have a set of states, which we're going to label C. So this is going to be, we're going to posit there's certain behavior being classified here, say smoking and non-smoking. That might be the set of states that we're interested in. Maybe another case it would be whether I'm sitting, standing, lying down, or engaged in some active movement. So it's a set of states, and then we're going to have a set of observations, which we're going to denote by a vector x, which is going to have subcomponents x sub 1, x sub 2, x sub 3, corresponding to particular measurands, corresponding to particular things we've measured. So maybe our x here consists of 3 elements of accelerometry, 3 elements of gyroscope, RSSI to measure signal strength associated with Wi-Fi routers, and then perhaps it also includes GPS speed and GPS accuracy. Alternatively, for your cases, it may include a magnetometer component, which might be relevant for detecting the fact that you're next to a big block of ferrous metal, like an engine. In other cases, what you might be interested in is Bluetooth signal strength, to figure out if I'm likely to be in the same space that I could exchange pathogen with Cheryl, for example. I might be looking at her Bluetooth signal strength relative to my own. Now, the assumption here in the naive Bayes context is that each of the components of this vector x is in fact independent of one another, conditional on being in a certain state. So given that I'm smoking, we're going to assume that the distribution of values associated with received signal strength indicator from a Wi-Fi router is going to be independent of my gyroscope readings, for example. Here, we're therefore going to, using the application of Bayes' theorem, we're going to be positing that, okay, the probability of me being in a certain state, C, given this state vector, which is composed of these subcomponents, x sub 1 through x sub n, is proportional to some prior distribution over C, where we say, well, okay, maybe you tend to spend more time not smoking than smoking on average. Without even looking at the data, you expect more time smoking than non-smoking, for example. Times this probability here, the probability of observing this state vector, or this set of observations, this vector of observations, accelerometer, particular readings for accelerometer, particular readings for gyroscope, for received signal strength, etc., conditional on my being smoking or non-smoking. So this is an application of Bayes' rule. And for those not familiar with Bayesian techniques, the basis of Bayesian techniques lies in the fact that we have this prior and we have this likelihood, and we can derive from that some posterior distribution over C, which is positing what's the probability that I'm smoking or not smoking. So this is an application of Bayes' rule. But with naive Bayes, what we do is we further impose a fairly strong assumption that each of these components are conditionally independent, given in being a certain state. So we're going to take this probability and we're going to turn it into this product of probabilities of observing a given output for a specific measure, say received signal strength indicator, given that I am sitting, or given that I am standing, or given that I am lying down, or what have you. What's the probability that I observe a certain signal strength indicator given that I'm smoking? What's the probability I observe, to assess the probability I'm smoking, I'm going to be multiplying all these probabilities for different sensors given that I'm smoking. And this probability here might be one that would be estimated based on some sort of multivariate normal, some sort of normal distribution based on a maximum likelihood estimate. So this would unpack to some sort of standard distributional assumption, would be a very common way naive Bayes would be done in a given statistical package. And there's further an assumption here, and this is very important for understanding the distinction from hidden Markov models, that there's no temporal dependence between the x's, these vectors, at a given time, except through the states. And I've been sloppy in my notation here. Really, I should superscript the t to indicate this is a vector at a certain time, and each of these are the subcomponents of the vector at that time, that specific time. Okay, so we're assuming that each measurement that takes place over time is independent of the others, except, conditional on me being in a certain state. Okay? If I'm in a sitting state, I'm going to be seeing a certain distribution associated with these that's not going to be varying. So a support vector machine provides us with one way of trying to estimate, to classify from a given data point, to classify whether we're in a smoking state or a non-smoking state, for example, based on this decomposition. And what's done then will be to impose a prior, and then you could use a maximum likelihood method, for example, to estimate the parameters associated with this distribution. In other words, that maybe for smoking there'd be a higher likelihood of seeing a weak signal, and a higher likelihood of seeing a strong GPS signal. For a support vector machine, we're doing something quite different. This is a more computational technique. It's a technique that causes me a certain measure of discomfort, but from a statistical standpoint, because it's a little bit too black box-ish for my comfort levels. But the idea here is that we have some data points which are labeled, and we are going to identify a hyperplane that is going to separate these in space. So we might have a 9-dimensional space. It might consist of, for example, three accelerometer, or excuse me, this would be six-dimensional, three accelerometer readings, RSSI speed and GPS speed, GPS accuracy. And we're going to try to find a hyperplane that sort of cuts between the data for non-smoking and the data for smoking in a way that most cleanly separates these. And there's some mathematics behind how you identify a clean separation that I won't go into here. But it supports identifying this sort of separating hyperplane that is going to divide those. And the idea is that things on one side of the hyperplane will be smoking data, and the things on the other side will be non-smoking data. So we're going to try to identify this division between the two. And there's more sophisticated variants that might use multiple hyperplanes and so on, but the idea is to geometrically separate these. And as you can see, with the data, once you visualize it in a higher dimensional space, there's often a certain plausibility for it. There's a clustering that goes on. So in this case, for an individual who is non-smoking, there's a clustering with respect to the dimensions here that lead to most of the non-smoking data to be grouped together and somewhat intermixed with the smoking data, but once again, the smoking data is a little bit more clustered. So there's this separation that might be natural. Now, in some cases, this can be very powerful, and Narges, to her great credit, has explored a number of different techniques for trying to classify data. One of the tools that we'll often use is a technique that's known as TSNE, or T-distributed stochastic neighbor embedding. The idea here is that it's a dimensional reduction technique. Given a 9-dimensional space, it will attempt to sort of establish a metric on that space such that we tend to group together clusters in an effective fashion in 3 space. Okay, so here there's been a naturally 9-dimensional space, accelerometry, gyroscope, each of which have 3 axes, received signal strength indicator, GPS accuracy, GPS speed. And using TSNE technique, Narges has reduced the dimensionality of this space to 3 dimensions. And as it turns out, the 3 dimensions that it captured by examining the structure of the data were such that they tended to neatly separate, on the one hand, the smoking data, and on the other hand, the non-smoking data. Now, having identified this reduction, then it's easier to identify a cut plane which divides them, a rule, as it were, for classifying one set and distinguishing it from the other set. So TSNE is a technique which is quite popular in clustering, particularly for high-dimensional data, and can be useful for identifying sort of subgroups within it, and may be quite helpful for then trying to identify a separating hyperplane. In this case, it was a highly successful exercise, to her credit. Now, a few words on this. You'll notice that this used 3 axes of accelerometer and 3 axes of gyroscope. It's not to be assumed that we'll always just throw all the data at it. And this has been the subject of some recent discussions with William and others about the degree to which we may wish to reduce the dimensionality up front by taking advantage of some of the symmetries involved and reducing accelerometry to, say, the accelerometry measures to just 1 or 2 measurements, or reducing the gyroscope to just 1 or 2 measurements. In this case, it came out quite favorably. In other cases, statistically, such as with naive Bayes, you may wish to identify a smaller dimensionality of space by essentially just taking, say, the norm of the accelerometry data. So in other words, rather than taking each of the elements of it in isolation X, Y, and Z as elements of this vector. We may instead want to use something like the norm of them, so the square root of x squared plus y squared plus z squared as sort of an element of the vector. There may be reasons for doing that for certain contexts that don't carry over to other contexts, and in general, it will depend a little bit on what you're trying to get out, the degree to which you could reduce these different dimensions. But generally, what you're doing here with these techniques is trying certain data items, seeing how well the classifier works in successfully delineating these different classes and iterating and trying to learn from that. Now, in Narges' case, she actually found surprising levels of clarity as being secured through these techniques. So this is some data from her smoking ground truth study, where she actually knew the underlying ground truth of the situation, and she took part of the data, and a technique that's quite common within the machine learning area. She trained the models on a certain subset of the data, identified plausible classifiers, and then she applied that data to a different subset of the data. And so she built the models using one set of data, and she tested them using a different set of data. And what she found actually was a quite high degree of classification. So here, unfortunately, the scales aren't so clear, but I understand this is 0.2, 0.4, 0.6, 0.8, and 1 up here. So she's getting up to quite a high degree of true positivity here, with a false positive rate, which is somewhere down around 10%. And although I don't have the data here integrated in the presentation, this is not the result of simply guessing that most of the time people are in a non-smoking state. It turns out that the statistics are rather different from that, and we are securing a fairly favorable classification mechanism using both of these classifiers. Narges also will sometimes present confusion matrices, which basically quantify, okay, how many false positives are there, how many true positives, how many false negatives, and true negatives within a matrix. And I don't have that here, but she's provided that in the past, which seemed to demonstrate pretty effective results from this technique. So I've been surprised at how effective the classification is, but this graph here with the TSNE reduction of this data is suggestive of a significant amount of clustering that these algorithms are probably taking into account. So I'd like to now talk a little bit about that third technique, which does take into account temporal context. This is a technique which we've made quite strong use of over the past few years, and in fact, to the point of building our own library, which has features which we couldn't find in any other libraries online that are commonly available. And this is a technique known as hidden Markov models. In contrast to the two previous techniques, this one does take into account temporal context in a very important way. And we're going to talk about why that's useful in just a minute and give an indication about what it means operationally. But the idea here is that we're going to characterize a given participant with respect to a particular classification challenge as being in one of several states. So they may be in an on-person state, for example, or they may be in an off-person state. In more sophisticated classifications, this may involve different postures that they're in, or different health behaviors within a broader set. And we want to classify a person at a given time point with respect to the state that they're in. So we want to classify for a given set of data that we receive at time t, or at duty cycle t, say a 5-minute time period over which we've captured data across the different sensors. We want to know was the phone likely to be, say, on person during that cycle or not? And in order to assess that, as for naive Bayes and as for the SVM, we're going to be drawing on data from multiple sensors, from multiple types of measurements. And we're going to be trying to combine them to yield the best guess as to whether they're on-person, off-person. So say during a given 30-second epoch, we have measurements, and I'm going to say we're in this epoch here. These are 30 seconds each. And for each of them, we're going to make some very, very simple measurements. We're going to measure a continuous accelerometer value as measured by a norm, a particular value. And we're going to further classify whether the phone is horizontal or not, whether it's placed horizontally, which can be determined by the phone orientation stream, data provided by the phone. You can determine whether it's horizontal, putting aside the issue of what particular direction it's facing, and in fact, whether it's plugged in or not. I'm just throwing a couple of these out here. These aren't particularly privileged. And the idea here, folks, that we're going to exploit is that, look, if the phone is on person, you're going to tend to have a somewhat higher accelerometry. Why? Well, because you're moving around. You may be walking. You may be sitting. You may be biking home. In any of those cases, the phone is likely to be jiggled and jaggled a little bit. There might be a bit of jiggery-pokery going on that's going to cause that phone to be moving around. Even if you're lying down or sitting, you might be moving in your chair a bit or rotating slightly. Yes, a given measurement might be low, but as a general rule, you're going to have somewhat higher accelerometry values. Now, in terms of if the phone is on person, it will quite rarely be purely horizontal. It'll happen sometimes. It may be that it just so happens that the way you're sitting places in a perfectly horizontal fashion, but more commonly it's not horizontal, and it's quite unlikely to be plugged in. Occasionally I'm known to plug in phones while they're in my pocket, but generally they're kind of hot potatoes. They become a little bit warm, and often I'll take them out. But I have been known to do it, but it's one of my probably more curious habits for those in the room. So what we're trying to take advantage of here is that for on-person state, we have some characteristics in how in terms of the accelerometry, in terms of whether the phone is horizontal or not, whether it's plugged in, that we're going to take advantage of. And we're going to contrast those with some similar measurements. For the same measurements, correspondingly sort of different tendencies when we're off-person. So we could think of these as dictating sort of a likelihood of observing a certain accelerometry or observing that it's horizontal, for example. And for off-person, we're going to formulate a similar set. So for off-person, maybe the phone tends to be have a smaller and probably a narrower, I haven't really represented it, but a narrower distribution of accelerometer values. Could it be, why isn't it always zero? Well, there's things that happen. People bump tables. The phone may be sitting in a backpack that someone nudges with their foot when moving by it or what have you. But the acceleration tends to be less. The phone will tend to be more commonly in a horizontal position. Not always. It may be sitting in a backpack at an angle, but it will quite commonly be in a horizontal position, and it's more likely that it will be plugged in. Typically, when I go home, I take my phone out and I plug it in, and that charges it up. Okay? So the reflection here is that in the off-person state, we tend to have somewhat different patterns on average than an on-person. But if you consider a given measurement, let's suppose that we know that the phone is horizontal. Does that mean it's definitely off-person? By no means. It's more likely to be. It's a lot more likely if we're off-person that it's horizontal than if we're on person. But it could be we're on person, it's just a fluky sort of thing. If it's plugged in, does it mean it's definitely off person? No, it is possible it's sitting in our pocket. But to get real insight from this, we'll do two things. The first thing is we'll combine data from each of these. The second thing we're going to do is we're going to take into account the temporal continuity. The fact that maybe right now the phone's acceleration is very, very low for this particular duty cycle, but in neighboring duty cycles it may be much higher. And we'll reason about how likely it is we put the phone down or picked it up. So here we have this 30-second epoch, and at the 30-second epoch of index significance, we have a medium level of acceleration. Okay, could be it's off person and just someone has nudged it. It could be on person and we're just in a somewhat more sedentary position. It's not horizontal and it's not plugged in. So the question is it on person or off person right now? Now, we could try to guess from these characteristics alone, and by summing up the likelihoods across, or by reasoning about the likelihoods across these different associated with these different distributions, we could try to come up with an estimate. But what hidden Markov models are going to take into account is what's going on before this and what's going on after this. And you'll notice that before this, it had a low acceleration in the 30-second epoch before. And successively later, it's also lower. So we might want to take that into account, the fact that, yes, right now we had a higher acceleration value, but in neighboring times, we don't have a high acceleration value. And we might want to take into account the fact that, well, phones do transition between on person and off person, but it's comparatively less common. Maybe once out of every 5 minutes on average, if the phone's off person, we'll pick it up to look at it, right? We'll pick it up and interact with it. Maybe if it's on person, about once every 20 minutes on average, we'll put it down. It's probably an overestimate, but the point is there are transitions, but they are associated with sort of slower time constants compared to 30 seconds. And we're going to take advantage of that. We're going to take advantage of the temporal continuity, ladies and gentlemen, associated with these measurements. The fact that they're not leaping around, we're not going back and forth between these in a very frequent fashion. So this is a hidden Markov model here, one that aspires to take into account three measurands. So how do we work with these hidden Markov models? Well, we have to identify certain components. We have to identify the set of states that are associated with them. Here it's on person, off person, right? We have distributions associated with observations, which are typically multidimensional. William's been working really hard on the multidimensional context down there, and he's heading for a triumph, but it's not quite in time to show it for this presentation. And then critically, and this is what's different, this is one of the things that's really different from the naive Bayes method that we saw earlier, that's a transition matrix that captures state evolution from one state to the other. So given that we're in an on-person state, we have a certain probability on a per minute basis or a per epoch basis of transition to off-person and vice versa. So we're going to maintain as an explicit set of parameters for this model, an explicit construct, what our assumptions are about transitions between these states. In other words, our assumptions about temporal continuity or temporal sort of orderliness of the data. Okay, so we're going to be keeping track of a transition matrix. Now, the assumption here, as in naive Bayes, is that conditional on being in a state. If you're currently in a state, actually, excuse me, this is different. No, there is a naive Bayes assumption. Given how we're handling it, it's going to be a similar thing that falls out. But here, given that we're in a certain state, our measurements from time point to time point to time point are going to be independent and identically distributed. So if we are sitting, the idea is, assuming we're still sitting, my measurements for the next time point, the next time point, the next time point will just be draws from some distribution that they don't depend on each other temporally. So the thing that matters temporally is what state I'm in short, not each particular measurement. So the idea is if I'm in a certain state, the acceleration may vary a little bit, but it's independent. We treat it as independent. Okay. And finally, the method does focus on these temporal regularities, so it's less thrown out by outliers. So the key thing we're going to take advantage of here is the fact that we know something about the neighboring points, the neighboring observations. And for that reason, we're going to tend to prefer interpretations that are consistent with these. We're going to take into account how frequently we transition between the states. And what I haven't done here is to provide all the math that takes this into account. It's not so fearsome, but it takes into account both your current observation and the distribution of probabilities you were in a given state in the last time point, and the transition probabilities. Okay, given that you were in a certain state in the last the last time point, what's the likelihood you remain in that state in this time, or what's the likelihood you're in a given state in this time point? So it'll take into account not only these data here, but the transition matrix and the probability that you were in a certain state within the last time point. I haven't included that here in my presentation, but that's all included in the analysis that goes into these hidden Markov models. So coming out of a hidden Markov model, what will we get? Well, we'll get a couple things. Most commonly, we're going to try to estimate two big things. One is the transition matrix, how frequently we change between states. And the second thing will be aspects of this distribution. For example, the mean and standard deviation associated with this normal distribution for that state versus for this state, or the likelihood of being horizontal or not horizontal. A hidden Markov model algorithm commonly through maximum likelihood estimates, will try to identify the parameters of the distribution and of the transition matrix that best fit the underlying data. And in that sense, it's what we call an unsupervised learning mechanism, like the naive Bayes we saw earlier. We don't have to tell it about the ground truth. We just run it on the data. It will try to deduce the state structure, the transition matrix. We tell it the number of states. It will try to deduce the transition matrix and the parameters associated with the distributions. In a very common context, though, we do have ground truth information. We have the sort of information Narges has collected, that Williams collected. We have information about the states that people were in at a given time, whether someone at a given time was on person, whether they were off person at that time. And we have the acceleration values, the plugged-in status, and the accelerometry values for those states. Now, when we have that, we can take this a level further. We can actually directly estimate these distributions from that ground truth data, or more typically from a subset of that we'll use for training. What that means is, from a subset of the data that's set aside for building this model, we will identify for each of the states, on person, off person, let's say, standard deviations and means, say, for the acceleration, the norm of the acceleration. We'll estimate the fraction of time that it's horizontal versus not horizontal, the fraction of time that it's plugged in or not. And we'll do that for each state in turn, for off person similarly. Now, we may further identify the characteristics of the transition matrix, how frequently we change between states. But often that will differ from person to person with some characteristics. People have different habits. So we'll often not put the big emphasis on that, but we may do so, and we may test that model. Having estimated these transitions, we may test that model against another subset of the data and see, well, how it predicts the ground truth information that we have to our avail, and use it to sort of assess how well this model captures the classification of underlying ground truth, take into account both movement between states and take into account these elements of the distribution. Having done that, having arrived at a hidden Markov model that has these distributions determined, whether from maximum likelihood methods or by direct estimation, and one which we have some confidence, we may then run it on unlabeled data. So this would be the sort of data that you're collecting right now through your studies here. We may take this hidden Markov model, run it on that data, and estimate just one item here, to wit, the transition matrix. How frequently people, this particular person, for example, picks up a phone or puts down a phone. And having estimated that transition matrix, we may then, using this hidden Markov model, derive probabilities for the likelihood that they're in an on-person state versus an off-person state for every epoch, for every duty cycle within that data. So what would come out of an HMM analysis there would not only be the estimated HMM model, but a labeling for the data within your data set as to the likelihood you're on-person or off-person for that particular time period. And in many cases, we just want to have one labeling, and there's an algorithm known as the Viterbi algorithm, which will go through and give you the single most likely sort of state for that point in time. So it might say on-person, on-person, or off-person, 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 on-person, off-person, off-person, based on the hidden Markov model's estimate. So you can use hidden Markov models in either way, either to give you a probability distribution for being in a given state at a certain point in time, or you can use them to provide a single most likely state that you're in at that point in time, putting aside any uncertainty. What that will mask is, sometimes that classification of on-person will be very confident, and sometimes it will be very uncertain. It'll be very uncertain as to the classification, whether it was on-person, off-person. So hidden Markov models are proving a real workhorse for us in terms of classification techniques. Many of those that we've worked on fairly successfully have been quite simple. And William's working on, and I know Narges is working on, and Rahim is working on right now, multivariate HMMs for several classification problems. But we've actually secured quite a lot of good results out of even univariate ones. Univariate ones that take into account, for example, accelerometer data. A couple cautions about HMMs. HMMs are very, very well adapted for eliciting this latent information, this information about whether someone's likely to be on-person right now or off-person in a temporal context, in a way that takes into account the regularities about how commonly people switch between contexts. So very powerful for estimating these latent factors, these latent states. But they do have some shortcomings, and I'd like to enumerate a couple of them. One of them is the fact that we are making a simple Markov assumption here that our likelihood of transitioning between these states is independent of how long we've been in the state. So, for example, if we've been in the on-person state just a brief time, I would argue that it's rather more likely we'll put the phone down than if it's been on our position for, half an hour now or an hour. There's a lot of picking up, looking at it, and putting it down. that a transition matrix like this is not capturing. It's saying, there's a probability of 0.05 per minute, a probability density 0.05 per minute. It's actually a probability per epoch that should be represented here. But that's not, it's independent of how long they spent on person. And as a result, it doesn't capture some features of the situation we know that are commonly plausible. Another factor is this IID assumption. If you are in the on-person state, the draws from acceleration are assumed to be independent and identically distributed. That might not seem so implausible, but this distribution is also assumed to be drawn from in an IID fashion, in a fashion that where each value drawn from it for each successive epoch is independent of the other, and that's a bit of a weak point here. Conditional on being in the state is making that assumption conditional on being a state is certainly a lot less bad than making it just assuming it in an unconditional sense, but it still strains plausibility. So, there is that straitjacket in terms of our assumption here. A further limitation to this, which is a subtle one in terms of how they're used, is if you were to run a model like this, say with two states on a given set of data that's unlabeled, that you don't have recourse to ground truth, and you're running in an unsupervised fashion, it's going to derive states, transitions between them, and estimate parameter values for the different distributions you've told it about, and estimate these elements of the transition matrix. But that isn't necessarily going to give you the states that you're interested in. Maybe you're interested in on-person, off-person, but what it may be deducing is whether you're indoors or outdoors. There's nothing inherent in the fact that you specified a two-state model here, and you specified some distributions, or you specified some distributional forms to take into account for several measurands, that's going to force it to elicit the semantics, the underlying sort of distinction in which you're interested in. To capture that, it is more reliable to work on some labeled data, some ground truth data that you have collected, where you actually can identify the parameters of this distribution, estimate them directly, and then run it on data where there is no labeling in a fashion that deduces transition matrix. Without that, you may be thinking you're deducing on-person, off-person, but you're actually deducing whether you're inside or outside, or whether you're on a vehicle or off a vehicle, another two-state HMM. So in short, with HMMs, they're great for estimating latent states, but if you really know which latent states you want to estimate, the likelihood of being on-person, off-person, you'll get quite a bit further, in my experience, by working with labeled data that you can train it. You can use to estimate these distributions, and then rely on the HMM algorithms for estimating the transition matrix. So those are some comments on HMMs. They are a very powerful, quite general, and a fairly accessible technique for doing classifications in this data, and they're probably the foremost tool in our toolbox for classifying states, for labeling the data. And indeed, I think some of the data that Kevin showed yesterday had labels derived from Williams HMM for example, for on-person, off-person status that can be quite useful. Okay. I'd like to talk a little bit more broadly about this issue of kind of estimation and validation. I should have gone to this slide first before beginning some of those remarks about the role of ground truth data. We have found ground truth data extremely valuable for developing reliable labels for the data we're interested in. And it's not terribly hard using IEPI to run a ground truth experiment. This is not something supported by Ethica's version of IEPI yet, but it is something which we put a lot of emphasis on, and I'm sure William could show you an interface for ground truth data collection if those of you who are interested. But basically it involves asking people to record for certain periods of time, often for shorter periods of time, when they transition between states or when they're engaged in a certain health behavior. Ground truth data of this sort, as I've mentioned, we can use to estimate statistical model parameters. We can use it to identify robust predictors for an underlying latent state that's not directly connecting the data. In short, to arrive at proxy measurements for that state. And to cross-validate those classification model results, we'll often set aside portions of that data that we'll use for just checking the predictions of a model built with a different subset of the data. A second major role is one I alluded to this morning, and this is the role of simulation experiments. I'm particularly referring here to dynamic models, agent-based models being of particular note. These are individually articulated models. A given person is represented in the model. That person can be represented in the model in a built environment, in a social network, could be represented in the environment as embedded in a school, in a neighborhood, in a way that would give rise to statistics similar to what you'd get through through hierarchical modeling techniques or mixed or random effects methods. And here, these simulation models can be valuable in assessing the reliability of the statistical models by placing this simulation model into a context where we collect similar data to what we do empirically. We can run statistical estimators or statistical classification tools against the data from this model and see the degree to which it matches what we know is going on in that model at a precise level. The key insight here is that in a simulation model, in a dynamic model, say articulated at an agent level, we have kind of a God's eye view of what's going on. We know the state of every person in that model. We know their history. We know their context, their history of exposures, potentially, if we choose to record it. And we can use that to then compare against what we've deduced through the statistical model. Even more so, we can use cases where there's a mismatch to try to refine the statistical model and to identify cases where the statistical model is highly responsive in terms of the quality of data it produces, in cases where it falls short, where it has blind spots. This is a very, very valuable use of dynamic models that doesn't require a model that's incredibly data-rich, just a model that has a certain degree of plausibility associated with it. And this has been a technique we've used for a number of statistical methods within our group. I had mentioned them earlier with Jushin here, with Kevin. It's also a technique that William has used back there early. I don't know if he remembers it well, but with AnyLogic early in his investigation of some hidden Markov models. We wanted to know how well they were picking up what was going on in the underlying model, so we'd test them against models created in the agent-based package AnyLogic that you may be seeing this afternoon. So here, he was using those things to test how well the HMM was picking up underlying features of the situation before then applying it to real-world data. Another technique that we've explored in conjunction with Jushin is what are called pseudo-residuals. And these go by the name posterior predictive distributions in the Bayesian literature. But basically what you're looking at is seeing how well the statistical model that you've created performs in terms of predicting possible outputs given a certain the parameters as identified by that model. So the posterior predictive distribution you are using the posterior distribution, you're deriving sort of synthetic observations, and you're comparing the distributions for those against the distribution for real-world observations. This is it's a tough thing to get your mind wholly around, but there's some good expositions of it. And the basic idea, folks, is that we're trying to make sure that the statistical model has certain face plausibility in the sense of generating data with distributional features that are very similar to those of the empirical data we observe. And these pseudo-residual techniques can be very readily used in R or other tools that help you use QQ plots or other plots comparing the empirical distribution from data gathered from the world with data gathered from the statistical model. So pseudo-residuals are a technique that don't depend on a simulation model, a dynamic model. Rather, they depend on you formulating your statistical model in a fashion that that will allow for identifying sort of posterior distributions for outputs. So those are all the comments that I have on this classification front. It's a front that we're working to advance with a number of classification schemes in which Narges and William are really helping to lead with some good work by Rahim as well. So I finished a little bit early here. Are there any questions? Yes, Kathy. That's a great question. That's a fantastic question. I stand here remiss for not having addressed that. So we did that. We've done it both on a per person basis and on a group basis, and William can talk about that. So we have applied hidden Markov models on a person-by-person basis at times, and we found that actually in terms of, my recollection is in terms of cross-validation for that same person, they exhibit greater classification abilities. But generally speaking, in terms of generalizability, if you have the model derived from a single person, unless you want to classify, well, okay, there's a very key need where that's really useful. Suppose you want to, and this is a study design technique, which we've used a little bit, you could say, in one context, but it's a more general technique. So you can imagine asking participants in your study for the first 3 days of the study to record carefully using one of these ground truth recording interfaces, when they take personal care products, right? You could ask them to record when they go outside and when they're inside. You could ask someone to record cases where they've been eating, for those first 3 days. And you might then identify from that first 3 days of data that are labeled, you might identify a hidden Markov model for that person. And after those 3 days, they have no obligation in this regard. They could be reporting no more ground truth information, but you know something about their habits, their patterns. You know something about their, in terms of the buildings that they're in and so on, perhaps characteristics of their home, things that would help distinguish for them whether they're indoors or outdoors. It might be a little bit different for someone who's living in a big apartment building and someone who's living in a house, say, a bungalow. And in short, if you craft it for that person, you might be able to identify more robust classification schemes for the rest of their data collection, which might last several months. And that could be very useful for you to identify points where they may be eating and popping up a survey for them, points where they maybe take your personal care product and asking them an appropriate question or what have you. So that's a case where it can be very useful to do on a per-person basis. If you are trying to identify more general mechanisms for classifying for whole populations on person, off person, you may get little leverage out of doing it separately for each person. You may want to, run a ground truth study on a one-time basis with 20 volunteers, identify robust measures, classifiers for on-person, off-person, and then run them on many different studies from then on with different people entirely. And for that, being able to arrive at a separate classifier for each person is not going to be that helpful, because you're not going to see that person again for later studies. And so for that case, we'd use a single classifier. But it is interesting because by doing it on a per-person basis, you can find some indicators as to how heterogeneous the underlying population characteristics are. So if you look at the gap in terms of confusion matrices between that indicate sort of the degree of classification that can be achieved, the accuracy of the classification between a per-person trained HMM, a customized HMM for them, versus one that's general, you will find some gap. And William could talk more about that, but that was probably an indication of the degree to which, a general mechanism is going to be, the degree to which it will be really helpful for classification in general. What's the gap in terms of classification? William, yeah.
I was going to say, you also were just talking about a combined approach.
That's true.
Generating the actual state distributions using ground truth data earlier on, but then on the data from particular phones, generating the transition matrix without any ground truth data from the phone.
That's a good point.
So you already have your state distribution from all
yeah. Yeah. I think that's a great point, William, and so the idea here, and I'm going to repeat it for the sake of internet listeners and so on. Here we're going to we might, for example, train these on data from people in general on a grouped basis. We're estimate these distributions for our model based on general patterns we see across the population. But then we'll have a specific model that we will train without recourse to ground truth data for each person within a study that would pick up their particular characteristics in terms of, say, their habits in terms of picking up a phone and putting it down, or in terms of going out of a house and back in, or in terms of taking vehicular transportation versus active transportation. We could do that, and we could use that to have a model, a per-person model for that larger study without the burden of doing a ground truth study for that person, but still have some measure of adaptation. That's a very good point, and one that is indeed a sort of a hybrid approach. So, other questions? Yeah.
So, in this kind of unsupervised learning, it's typically done using local optimization algorithms. So basically, they're not going to give you a global answer. They're going to kind of pick a spot and try and converge to a single error. Most of the ones in this field are the classic ones are based on variations, expectation, maximization. You're familiar with that. The neat trick, though, is you can actually seed the initial graph, the initial model, with generic ones trained offline.
That's true. That's a good point.
Unsupervised learning to tune it. You basically bias it. It's like a method or something like that. Your starting point is selected by the one you built with training data, and then you can optimize it individually unsupervised. The assumption that probably the starting point is going to get you close to where the person's behavior is, and then you're going to tune it to that particular behavior without the.
That's a good point. Another thing that I've oft wanted to explore with Jushin and probably will in the coming months is applying a technique like MCMC to actually sample from the parameters of distributions here, which might give you some it would go beyond the sort of maximum likelihood estimate where you're just getting one parameter value estimated as the mean and standard deviation here. You might actually be able to sample from distributions of parameters and state transition probabilities to arrive at sort of a more robust sort of probability of being in a given on-person, off-person state for a given epoch, for example. And I think there's nothing to prevent that from being done. Hidden Markov models are fairly lightweight computationally, but when it comes to estimating some of the parameters, with maximum likelihood estimates, we have found that often we need to run it again and again and again and again to arrive at to deal with the issue of the local minimum. And I think Kevin's point about sort of seeding that initial point based on more general models is a really good one. So other questions? Yes, sure. Yeah.
Forward through time. So
right.
It's connecting the individuals in an order. It's connecting the
observations in an order. This is totally unordered with respect to observations. Each of these data points. So this technique could be applied. It's a great question. This technique could be applied on a per person basis, where every one of these dots would be a particular observation for that person, and these would be observations that happen to be smoking observations. These would be not. It could be applied in that way, or it could be applied on a cross-population basis. I believe this particular one is on a cross-population basis. So
it can't be done on like a multi-level basis where you're combining your data, but you're keeping track of
I'd be intrigued by talking with you about that. I mean, I don't see any reason that one couldn't tag things with an attribute saying from whom was this data point derived and use that. So I see what you're saying with sort of multi-level modeling. I think that's an intriguing idea. And yeah.
Pretty much every classification algorithm has a hierarchical.
Yeah.
Okay, so you can account for
yeah.
that.
Yeah, and way back 25 years ago, I was using a hierarchical clustering algorithm that was also quite powerful, although it hasn't been widely circulated since. But yeah, there is some potential for imposing hierarchy in these sorts of analysis. And I appreciate Kevin's comments on that. So a very important reflection though is that it does not at all consider the temporal ordering. The temporal context is totally missing here, right? There's no attempt to sort of capture the fact that if I'm in a car now, I'm likely, or if I'm in a vehicle now, it's unlikely that I'll be out of that vehicle, in the next 30 seconds. It doesn't really try to capture that continuity. It just jumbles them all together.
One last question for the Markov stuff for the temporal ordering.
Yeah.
Improving the predictions, is there any way to look at T-2, T-2?
Yeah, it could be done. Yeah, mathematically, it wouldn't be atrocious. It would add texture to it. I think it's an intriguing idea, but just like with autoregressive models or something, I guess there'd be a certain amount of gain that you could get through that. So. Yeah, that's a neat idea, and that would go in a way towards helping to reduce this vulnerability to sort of the assumption this is memoryless, right? That no matter how long you've been here, you have that same chance. So in other words, if last time step you were likely to be in state A, but 2 time steps ago you were in a different state, you're more likely to be in a flux here. You're in a different state than if that weren't the case. So yeah, I think that's an interesting idea, and I don't see why it would be terribly problematic. In fact, there are variants of this, of HMMs, which put aside the memory list restriction. I think they're called semi-Markov models. And I believe Winchell has actually done a little bit of work with them. And those have some extra. The algorithms are more complicated and a little bit less transparent. Math. You have to wade through more math, but I think it is possible. A very nice book, which I would recommend on this. I would recommend very strongly, and which actually ties together some other remarks here, such as on pseudo-residuals, is this book by Zucchini. It's called Hidden Markov Models for Time Series. And it's a very, very nice exposition of their use for time series data. There's a lot of literature out there on hidden Markov models, but much of it is for sequence data in bioinformatics, where the sequence is not one temporally; it's one in terms of particular nucleotides or amino acids or what have you. So this book by Zucchini, which is in our library, available electronically, and has a very nice sort of tutorial and step-by-step exposition, and then some chapters on applications to particular examples, and finally discussions on generalizations and sort of extensions of the hidden Markov models. I would recommend. They had a library as part of it, which was written in a fashion that caused me a certain amount of distress. But we've overhauled it and extended it greatly. And William is sort of the king of that library right now. And he's been working. He's modified it to support multivariate distributions, to draw data in from databases, to do cross-validation, and generally sort of made it much more general and useful for with the sort of data we're getting out of IAPI in a really rich way. And if anyone is interested in that library, we could talk about sharing it. Our hope is to release it as an R package sometime with collaboration with Jushan. So other questions? Yeah, Daniel.
If we take a step back, like how do these methods relate to things that I'm more familiar with, like principal component analysis, factor analysis? It's basically the fact that these are a little bit more flexible in terms of nonlinearity assumptions, or am I missing something completely?
Okay, so I've worked quite a bit with PCA, including in health contexts, and PCA is a fine technique, and it can be used in ways that have some similarities. Like the first two techniques of which I spoke, it is not PCA is not a principal components analysis is not a technique which takes into account temporal context. It'll analyze set of vectors. It will analyze the data to try to give you a set of principal components in a way that puts aside time. There's no representation of time there. But it's very powerful for identifying sort of for doing a sort of factor analysis in the sense of identifying hidden structures that unite multiple variables and might lead them to covary, right? Might lead several variables to covary because they really pick up some issue like my nutritional awareness, and that affects my eating of fresh fruits and vegetables. It affects my eating of red meat. It affects the degree to which I watch calories or whatever. It affects all of those. So there may be certain explanatory variables that are not limited to a single survey item, but rather explain many survey items, right? And PCA can be great for identifying those. What it doesn't do, and as such, it's sort of picking up some latent features of the situation. And so at that sort of very high level, it has some similarity. But what we're doing here, the task that sits before us on this juncture is a little bit different. We're trying to classify a person into one of a set of states at a certain moment in time, and preferably in a way that that does not only take into account multiple sensor measurands, but also the temporal context. And that's a little bit different. You know, PCA will elicit sort of common patterns of covariation maybe between sensors, but those won't necessarily map onto sort of underlying latent states, sort of health behaviors, or health states or contexts. They could in some cases, but generally speaking, from my experience, they don't. Now, as you know, PCA is also encumbered by linear assumptions, and there's some generalizations in ICA, the independent components analysis, that try to put that aside. But it's really getting at something different, and I view it as kind of a favored tool. I have used it for some things, again, related for clustering. I use it for dimensionality reduction. If I have a really high dimensional, so I'm using the CCHS, right, and I have a couple hundred questions of interest to me, I might use PCA to kind of identify principal components that covary across those, and then cluster in the in the three-dimensional space associated with the three biggest principal components or something like that. And we've done that with the CCHS and with other instruments for it's the CCHS, really, that's right, which is to very good effect. But I think PCA it's after a rather different thing. Here we're really trying to understand the underlying state that gives rise to sort of certain distribution and how that state changes over time. Kevin, I know you've also used PCA a lot.
Yeah, I think I go back to the higher level. The short answer is like this. It's all weighted sums. At the end of the day, there are a number of equivalences. The things that are familiar to you as kind of a classic frequentist, to the Bayesian formulations, to the distance space formulations that SVN uses. When we approach them from a Bayesian or distance metric kind of point of view, it's really just about the mathematical tractability. You can kind of then back it out and say, okay, well, this is really a kind of very specialized version of this other kind of statistical process that you're familiar with, but getting to that from there to here would require all kinds of somersaults mathematically, and if we adopt this other kind of more elegant, for this particular space, nomenclature and notation, you can kind of get there in a more elegant way. And so I think that, and the book we use in the machine learning class is
Kevin Murphy.
And so he's a hardcore Bayesian, but he actually does go kind of at the end of every chapter and say, okay, so if you're a frequentist, you might have heard of these things, and they're basically mathematically the same. Right, so there are equivalences, I guess, is the point, and we're not throwing up all the stuff you know.
That's true.
Often more elegant to do it these other ways.
Right.
Right, and I guess the question was less about the Markov models. Obviously, those are very different, but the other two methods that don't account for time.
Oh, okay.
How is PCA similar or different when really, you know, like to me, at a high level, it looks almost exactly the same. They're doing the same kind of thing. Yeah. They're doing the same kind of thing, but it's a different machine, and you get different answers.
Right, and TSNE, I think, is a model that's sensitive to nonlinear factors. I don't think it's straitjacketed into the linear set of assumptions. I'd have to go back and review from my reading of it, but I think it avoids some of the pitfalls that if you impose the linear assumptions associated with PCA. I mean, PCA indeed can be used to try to do dimensionality reduction and then identify clusters in that. It's just it does have some defined assumptions that are pretty strong on the linearity front. Yeah.
Are there challenges associated with there may be a third variable that compounds or moderates the relationship. So just using the on phone, off phone, for example.
Right.
I'm sure those three measures look very different, say, if you're a woman or a man.
Yeah.
So we carry phones in our pockets, and women tend to carry phones in their purses.
Yeah. Yeah.
Or living in an apartment versus not.
Yeah. So I think you're asking really good questions, and I'll answer you as a learning practitioner. We do see indications of that, and how do we handle those things? Well, one of the things that one of many things I've learned from Jushin is to try to spot indications of heterogeneity in these states based on the distributional the empirical distributions associated with them that might cause me to say split these states, divide them up to recognize that there's like with men and women, off person I'd argue is probably a little bit different. Is more similar to each other than maybe the on person readings. Yes, it's true. If it's a woman's phone, that it may be more likely to sit in a pouch than if it's a man's, where it's more likely to be put down on a counter. But I don't know that's really most of the time true. I think maybe the on person. What we would often see when we're using these methods, if there is some really pronounced heterogeneity within the group, is we might see two distribution, overlap of two peaks here or something along those lines. Some indicator that a single mode distribution is not going to be adequate, and so we might explore unparsing this into several states, or at least two, for male or for women or what have you. Or we might look at the hidden Markov models identified for different subgroups of the population, men and women, and compare those to each other, or indeed look at the ones on a per person basis and see how they differ from each other. I would say I wish I had a truly general, systematic, and rigorous sort of way of dealing with these things. It's just, in my experience, a lot of it is based on kind of examining the accuracy of these measures, seeing where it falls short, seeing the people for whom it works well, where it doesn't, or seeing aspects of these distributions and making appropriate decisions. But I don't feel that my comments there are fully responsive to your question, because I do think what you bring up is kind of a deep additional point. And that mediating variable may be a latent variable that we can't measure so easily. That's not easily observable, or it may be a variable that we know from participant characteristics, from demographics alone, that we may pick that up. In which case, I think that the situation maybe is a little bit easier in the sense of we could take into account explicitly within our handling of each person's data. But I don't know that I've done justice to that, but I hope those comments have some use.
Yeah, I see this, the HMM method.
Yeah.
Again, it's almost tailoring the classification to that individual, or to what's come, in the past. And I find that more interesting or stronger way to classify.
You can apply it, to each person, and you're certainly going to be training it off of particular time sequences. There's no question. So I do think it's fairly powerful in capturing those longitudinal features of the situation in the sense of that temporal context, rather than viewing each data point as its own solitude, right? Yeah. Other questions? No? Okay. Yeah. So let's take a break here. That's great. Mm-hmm.
Do you want me to do that now, or do you want me to do it at lunch? Or after lunch, sorry.
I think probably do it now. It's good.
Yeah.
Good. Yeah. Yeah. Let me stop the recording here. Yeah.